we discussed 3 ways of solving constraints: analytical, procedural, and numerical. This video will focus on another type of numerical solver, called a spring solver. A spring solver is actually a specialized type of particle solver. Conceptually, a spring system consists of a set of particles connected by springs. Moving one particle will deform the springs connected to it. This will exert forces on the other particles which will then have an impact on their position. Spring solvers are a popular framework for simulating many special effects, such as hair and cloth. The basic rules of the system can be understood by looking at just one particle. Each particle will try to stay in equilibrium. If it is not in equilibrium, then it will move a small amount in order to bring it closer to equilibrium. The movement in each iteration may be very small. But over multiple iterations, all particles will start moving towards equilibrium. The springs in the system follow Hooke's law. The law states that the magnitude of the force is proportional to the deformation. Deformation is defined as the difference in length between the rest state and the current state. Resolving the different forces can be performed using vector algebra. Simply adding up the different forces acting on the particle will give the final force vector. If the particle is in equilibrium, then the final force vector will be the zero vector. If the particle is not in equilibrium, then the result will be a vector with a magnitude and a direction. This vector will then be used to move the particle. In our example, the problem is a form-finding task. The aim is to find an efficient structural form, called a catenary structure. A catenary is the idealized form generated by hanging chain structure. The chains are attached at key points, and the structure is allowed to hang under its own weight. This will create a U-shaped type of structure. If this structure is inverted, it creates arches or domes that can be structurally efficient. In the example, we want to create a catenary dome. The initial state consists of a polygon mesh, lying on the xy plane. Each position in the mesh represents a particle and each edge represents a spring. Note that for polygons with shear edges, only one spring is assumed. The solver then adapts the positions of the particles. The initial state consists of the polygon mesh. The corner positions are defined as being fixed or anchored. All other positions are free to move, under the constraints of the springs. All positions are also subjected to a constant upward force. This force results in the system being out of equilibrium. As soon as the solver starts iterating, positions will start moving up to try and attain equilibrium. Over many iterations, the final form will gradually emerge. The images show how over time, the positions are moving upwards.